Well, let's talk about the coherence check.
Oh, yes.
So I'm going to open up. Let's see here. See what branch I'm on. Okay, I'm on some branch. Has this been merged yet? Let's take a look. Oh, there's a bunch of pull requests. How exciting. I guess I'll merge this branch and just start something from master. Let's fetch and what the hell is this? Get fetch. Okay, branch create origin main 2022-08- coherence. Yeah, so we wanted to get around to modeling negative impulse, but before we can do that, we kind of need to have the coherence check, I think, a little more accurate. So maybe we can start with currently we have the orphan rules, which are incomplete, and we don't have any overlap rules. Yeah. So we could, oh, hi, Dominic. Maybe it's more exciting to look at the overlap rules, because that's what the negative impulse would also be concerned with.
Yeah.
Dominic, I just saw that there were various pull requests by you, which I will look at later. But we were going to look at the orphan and coherence check a little bit. So we'll start by making a new, well, let me just page some of this back in. So we've got this, this is the main checking, like, judgment. It says the whole program is checked if all this stuff is true. And one of them is that we check every crate item, which is defined here. And here's the rules for checking different items. So one of the things we check is that each impl matches the orphan rules. And that goes off into a type judgment defined here, which is jump to def is very slow. Doesn't matter, defined here. But for the overlap rules, actually we have to check every pair of impls against one another, right? Mm-hmm. And we check, well, I think we check every impl defined in the current crate paired up with every impl defined in any other crate. So you have to check. So if the current crate defines no impls for a given trait, then it doesn't have to do any checks. But if it defines one impl, it has to check it against all the other impls it can see, even those from parent crates.
Right.
So the very first thing we have to do, like, that won't fit into this judgment because this judgment just checks one. Well, I guess we can make it fit, but it checks one item at a time. And we kind of need to assemble a list of pairs, so to speak. But we can do that by, we have also the full program, which includes all the other impls. So we can add a little check here. That's like every time we encounter an impl, we'll check the overlap rules for this impl. Right? And you know, we can start out with a dummy rule that's just always true. So this isn't very interesting, but we have to do some imports, I think. We have to import coherence overlap dot racket. That should work. Shouldn't make any bugs nor fix any bugs. And maybe we can add a test before we go further of something we, you know, expect to sort of work. Like here's some orphan tests. So we can make a coherence overlap. So for example, we want to make, we have a trait, we have a struct, we have an impl declaration for this struct. So we want to say that, you know, 2 impls for the same struct is an error, for example. And then we can also make one like implements trait A for any type T. That should also be an error. Maybe we'll add another struct B, or no, should add one like, but actually what I'm gonna do is just gonna inline these. Rather than putting them up here. But if we have, let's say 1 for struct and 1 for U32, that should pass. Start with that, real simple. And I guess if we run this test, source, Rust test, coherence overlap, we'll see a test failure because right now I don't see any reason why this would be rejected. And it says it's supposed to be rejected. Good. Okay. So let's see if we can make it fixed. So what we want to do, first thing is we have to find, this is an interesting problem. We have to find this may not be the right place to write this logic because we have to find every pair of impls. And right now we've got an impl here and we have the full program. But if you have literally the same impl twice, like we can go look in that program for all the impls that appear in any crate easily enough, but we can't tell if you have the same impl twice, we're not going to be able to tell that you have it kind of twice. Do you see what I'm saying? Or maybe we can. Let me show you what I mean. So we've got the full program where we have here one impl and we have here this decal program. And if you jump over to the grammar of the Rust grammar, I guess that appears probably in the decal grammar. So a decal program is a list of crate declarations and the ID of the current crate. So it's kind of annoying. What we can do, like trying to think how we can easily extract the full list of. Okay, there's two things going on in my head. One of them is it's kind of annoying that I might prefer if we change our representation so that it's not like an unordered list of crates, but that it's always the last crate in the list or the first crate in the list, one or the other, that's the current crate. It would just be like marginally easier. But ignoring that, we can easily match across all the crates by doing this. Right, we have, oops. Oh, sorry. Okay, we have this. This is the definition of a decal program. So we can match it here. And then we can replace a crate decals is a list of crate decal. Right, and a given crate decal is a crate ID. And a list of items. And a list of items is just like that. And then here's the given items we might find. But let's stop for a second. So at this point we've got we can kind of make a list, right? This is kind of annoying. Not sure why this is giving me a little warning thing. Okay. So this would pull out all the items in any crate and put them in one big list. Now, what we can do, we want to filter it down to just the trait items. Right now we have any kind of crate item, but we want to get it down to just the crate, just the trait items. We don't care about the rest. So filtering is kind of annoying in Redux, but the best way I've found is to do something like this. You write a function which takes a crate item decal and returns a list of trait impl decal. And what we're going to do is we're going to return either an empty list or a singleton list. So we define these two cases. If we're invoked with a trait impl decal, we'll give back a list with one item. And if we're invoked with some other kind of crate item that doesn't match this pattern, we'll just give back an empty list. And then, here we go. And then we can do something like this. We have this list of crate items. We can apply this function And let's do it like this. It's getting a little confusing. Lots of dots. Let's make a meta function for this. We'll call it all trait items. Decal program. So this function is going to return all the trait items. When it's invoked, it's going to get a decal program. It's going to begin by extracting all the items of any kind. It's then going to produce, I'll just do it like this in multiple steps. Produce a single list of all the crate items from any crate. And then for each one of those, we're going to map basically this select trait item. Okay, let me show you what I just did. So this function, the select trait item, takes a single crate item, which could be anything, and returns a list of either empty list or a one item list, right? And here we're using these crazy patterns to say for each crate, and then within each crate for each item, and kind of flatten that list and get a big list of all the items from any crate. And then we're going to apply this function to them so that we get back either like empty lists or lists of trait impulse. And then we flatten those two lists, and now we have filtered out just all the impulse in the crate. Does that make sense?
Yes.
So finds all the trait impulse in any crate. And notably, we don't deduplicate this list. So if the same thing appears in there twice, we'll get it twice. It seems like we have a problem with our parentheses, but I think that should solve it. Okay. So get a list of all the crate items in any crate. Filter that down to just the trait impulse. So this is given a crate item returns either if the item is a trait impulse, return a one element list, else return an empty list used for filtering. Okay. So now we can use this function. Trait impulse decal. I have a question, which is, would it be helpful, or does anyone want to try to drive this? Or is that too crazy? I feel like I'm typing fast, but I feel like I might, especially Santiago, if you were thinking of maybe picking this up, might benefit if you had to actually type. Although I don't know if you have the setup to do it.
Yes, I need to set this up. Yeah, I'm gonna do this like right after the call. Yeah.
Okay. So, right. So now what we have. Okay, this is how we're going to do it. Let's see. So we've got.
Could we use a similar filtering function to only filter trait impulse which exactly match the one given?
Yeah, I could.
How many we have? We have more than one.
Yeah, I was thinking what we could do is we could do that, or we could. So Racket gives you the ability to do some, equality and not equality checks, right? basically what I was thinking is, if we know that this impl has to appear at least once in this list. So we could find all the things, we could find the first such appearance, or any such appearance really, and then find all the things that come before and all the things that come after. And if it appears more than once, it'll be in one of those two lists, right? And so as long as we pair it, I think it doesn't actually matter kind of which one it originally was at the end of the day. But I'm just trying to remember how you write those patterns. I guess in particular, I think it's going to be a little I don't know if there's a way to say, how do I declare that I want the first one? So I could do something like this. I could say, right, and now I'm saying, find all the trait impls that before it, find this exact impl, and then find the ones after it. The problem is if it appears more than once, this is going to match more than once, I think, and run the same code twice. I guess maybe we don't care. So what? There's probably a way that I don't remember exactly how the little pattern matching stuff works, but there's a way to kind of say these two are not equal as well. Why don't we do this? Let's say we'll select all of them. Let's ignore the problem of duplicates for the moment. And then we can have a judgment that's like, impls, I don't know, not overlap. Impls equal or not overlap. We'll just call it that for a moment. It's not a very good name, but, and we'll check something like this. So this will say that for all the impls, they're either equal or they don't overlap. Then we'll deal with the equal case later. Because basically it's an error if like literally the same impl appears twice, that's just an error, right? So we should be able to express that somehow. So then we can define this judgment. And we'll say, yeah, when I'm I get so annoyed when I'm working on over SSH, the copy and paste sometimes does not match up. Like I hit copy and it takes a long time to actually take effect, or I don't know what happens. Something does. Anyway, so this rule will say, two exactly equal impls are okay. Or in particular, we want to say, we are checking the first, I guess let's make it the first. First impl against every other impl in every crate, including itself. So if we see a comparison of two equal impls, we assume it is the same impl being compared against itself for now. There is a separate check that you cannot have two exactly equal impls. That check doesn't exist yet, but we'll add it later. Well, here, except 2 equals if they are exactly equal. This is a bit surprising because 2 distinct exactly equal impulse overlap by definition. The reason is that, yeah. I think you're right, Dominic. We can use the same filtering trick and do something like where there's a list of exactly length 1 that sort of where you filter down to only impulses that are exactly equal to this, and the result should be of length 1, something like that. Anyway, so now we have the more interesting case where there's 2 impulses. And I guess the next thing I would point out is we haven't actually looked at what we don't really want all trait impulse. Actually, we want all the impulse of the same trait, right? And I think we should express that because it's gonna, otherwise when we try to debug, it's gonna like overwhelm us with annoying stuff. So what we can do is say a trait impl decal is actually this. So when this function that gives us all trait impulse can really take a trait ID. And this filter can select trait item given the trait ID. And now it's not just any trait impl, it's specifically those where this trait ref, what is a trait ref? It's been a while. I think a trait ref is just the pair of a thing and parameters, right? It's in a different file. Trait ref. So, right, so now we're matching against the trait impl. We're saying it has to be an impl with some parameters, but for this specific trait, right? And I can actually just turn a lot of these things into underscores because we don't care about them. So given a crate item, if the item is an impl of the given trait, return the 1 element list. And here it says find all impls of the given trait in any crate. And let's call it all impls of trait. And then we can call that here all impls of trait. Annoyingly, we have to kind of extract the name of the trait here. Okay. So now we are extracting the name of the trait, extracting all the impls of that trait. And I'm not sure why this is in a list. That's not right. All the impls of the trait. Getting a big list of impls, and then we're matching across them. So now we know that these two, they ought to be of the same trait for sure. So this basically is where we get into the interesting logic, because now we want to say it's true if they can't be equated. So we want to prove that trait impl decal 1 and trait impl decal 2 do not overlap. That's a little bit complicated. And I'm realizing we don't currently have, I don't think we have a negative judgment. Is that right? Or like a negative goal? Like we can only prove positive things? Which is maybe okay, but maybe we want to add it. I have to look. Like right now in the logic solver, our goals, right? We can have ambiguous goals, or we can try to add them or combine them or add implications, but we can't say that a goal is not true. So what we can do what we do in Rust today, where we have the same property, which is we basically have two ways. We can either tell it to prove something is true, or we can tell it to find all the solutions, and then if there are none, use that, derive something from that. But let's start with what we have to prove. I'm going to start by breaking apart these trait impulse into kind of into their pieces. So we don't care about the items, I don't think. We've got the two trait impulse, and they have Santiago. Do you remember we wrote down for the negative, maybe it was in the RFC or something, we were kind of re-expressing the coherence check in some hackmd somewhere.
I think like maybe it was in the RFC. Let me grab that.
So I remember we structured it a little differently than how the code had it initially, at least.
Let me see.
All right, so I think the first way that this could be true, if there's no way for their types to be equal, right? And trait ref is really trait ID and parameters one. Come on, stop. Fine. We know they're of the same trait, so we can just assert that. What we want to say is that these parameters actually, maybe we can do a, oh no, never mind. I was going to say maybe we can make a judgment that's true if they overlap and then do like a not provable, but I don't think we want to do that because it's a little more tricky. What we want to say is something like, if there's no way to equate them, this is what the current code does. It's something like, if parameters, or the current code does something like instantiate kinded var IDs 1 and 2 existentially, try to equate parameters 1 and parameters 2. If that yields an error, then there is no overlap. And then it says, if it doesn't, then check whether any of by formulas 1 or 2 are sort of known to be false, which is a little complicated. And then we were adding for negative impulse, like an extra couple of cases here. All right. which worked kind of differently. Sound right? So one way to do this okay. So let's look at I think the solver currently is a judgment for improved top level goal. What's this? So there's this prove goal thing that is true if the goal is provable. And I'm wondering, I think there's also yeah, this is a judgment form. So in Redux, there's like the two modes. The meta functions are just sort of regular functions, and then the judgment forms are more like Prolog predicates that kind of do search, right? And so if you invoke one, when you can check whether a judgment holds, and what you get back is like a list of values for which it holds. And if that's the empty set, then it doesn't hold. And somewhere, which I'm trying to remember, I wrote some kind of code. I guess it's here. Here it is. So what this function will do, extract schemes, is it takes some environment. It tries to prove something at some point. Let me see, where does it do? Oh, I see. This is more used after the fact. The idea was, let's see if I can find an example. No. Test scheme. What does this do? This is just a test. Maybe I'm not using this anywhere. I guess we don't have any code that sort of says this is not provable. But we're gonna have to add that. I thought we did it somewhere. But in any case, in Rust C, we have the idea of the kind of built-in unification code, and then the trait solver. And that maps to this idea in MIR Formality of relations, which are kind of built in, and goals, which are not so much. So we can try to prove that one type equals another, and what we'll get back is either an empty list of things, or we'll get back some constraints for which it is true. So I think what we want to do, let's try this for now. Here, we can make a so jumping back to context, we want to show, we'll start with this. We want to prove that these parameters, see if they're equal or not, right? And it's only want this to be valid if they cannot be made equal. So we have to create, for each of these kinded var IDs correspond to the generics on the impl. We need to instantiate them with inference variables and then try to unify, essentially. And the way we do that is, let me try to remember. Yeah, instantiate quantified. So we need to make an environment. That's the very first thing. And how do we do that? I don't remember. Environment with crate decals. That sounds pretty plausible. No, that's some other thing. That's just in the documentation. That's not in the real code. Environment with program. Environment with hook. No, 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 no. I don't remember. I haven't looked at this in a little while. So somewhere, maybe it's in here. Environment for create decal. That looks right. Environment for decal program. Okay. So what we're going to do now is we're going to get a base environment for our program. This is like creating a new inference context in Rust C. And then we're going to instantiate quantified. So this function takes in a starting environment, which will be a base right now, and then a quantified thing. So we're going to say quantified means like, well, that there's a quantifier. I don't know. Does that make sense? We want to say that there exists. No, let's make these. We're going to take this list and break them up. So where we had a plural, now we have we're matching against the elements. So now we can make a combined list of all the IDs from both. Oh no, that's not really right. Let's do it like this. Hold on a second. Let me just type this out and then I'll explain. So what is this doing? So these are the generics that are in scope. And these other things are the parts of the impl, right? So I'm creating this. There exists some generics. And then this little like term is stuff that references those generics, right? And when I say instantiate, what I'm going to get back is a version of this where every reference is replaced with an inference variable, essentially. So let me make a example. Imagine impl1 is impl for all t, let's call it debug for vec of t, where tdebug. Then, right, so kinded var IDs 1 will be, it's going to be a list of type t. And, well, trait ID will be debug. Parameters 1 will be just a list of the parameters, so vec of t. And by formulas 1, those are where clauses, the weird name that I've given to them. They're like the lowered form of where clauses, will be tdebug, right? And so the key point is these things reference t. So here, when I instantiate with inference variables, so for our example, we will get back, we will create a inference variable $t in the environment env1 and get back parameters 1 inf will be, if before it was vec of t, now it's going to be vec of $t. And same with this. And then we can do the same for impl2, except that our starting environment is not the base environment, which I'll call env0. But rather this environment one. Okay, so now we've instantiated everything. And so then we can make a goal. This is the thing we have to prove. And it's going to be like this. We're going to take each of these parameters from the first one and the parameters from the second one. And we're going to match them up. Parameter 1 inf equals parameter 2 inf. Dot, dot, dot. Yeah. So the and is all the following things in this list must be true. I think it takes a list. Then you know the parentheses. And then the things in the list are that the 1 has to equal the 2. And then we just try to prove it. This is the part we don't have yet, though. But let's see. So I think we'll make a really simple thing here for now. That's probably not good enough, but we'll call it cannot prove goal. Oh shit. Cannot prove goal in environment. Let's call it that. So given an environment and a goal, we'll check that we cannot prove it. How do we express it? I think we need a meta function actually. Because if we just do this, this is sort of exactly the opposite of what we want, right? This is saying we can show that we cannot prove the goal if we can prove it. So I think we need to write a function that's like no solutions. And so the idea is this will say, this is going to have to cheat a little bit. And we're going to, I'm trying to remember now how this works. Right. So this is getting into the weeds of redx. But like we have these judgments and we have these meta functions that are pure functions that always return a result. And these return many results. And there's you can't like connect them directly, but you can call this function judgment holds. And I don't remember exactly how it works, so let me look it up. Let me share this window. But basically, it's not a, it's like a not, how do you say? It's a racket function. It's not part of the pure, it's kind of like calling out into the base racket level because it doesn't fit the pure mathematical set. Or hold on a second. Oh, there's a question in chat. Oh, the negative impulse RFC. Yes. Let me share this. All right, so usually this is the redx reference, docs racketlang.org. And I look stuff up in it all the time. But judgment holds. We'll check whether this is true for any assignment of the variables. And in the second form, which is the one we want, it produces a list of terms by instantiating supplied term template. So what that means for us to pull back up our screen is is this right? Yes. Okay. So this is going to try to prove this, which says this weird name is the name of the solver. Invoke the solver on the given environment with this goal. And if it comes back with anything here, like env out, that's a success. That means it succeeded and it created a new environment that contains whatever like constraints or bindings on the inference variables or whatever else had to be true for this goal to be provable. And then this thing just says, we're going to make each time this is true, that's going to give us a new value for this variable. And then we're going to make a list where we instantiate this pattern with that value. So this is going to yield a list of solutions, each one of which is going to be an environment, right? So if it was successful, it could be like environment 1, environment 2, environment 3. But we're going to check that it's an empty list. And I guess we can actually, we don't really need the helper function to do this. We can actually do this here. It's just weird. I think you write it like side condition. And we're going to check that this is an empty list. So basically how we write our cannot prove goal in environment is by saying, find all the solutions. And if that's an empty list, then we can't prove it. And this is okay, is empty is probably not how you, I don't know, how do you ask for an empty list in Racket? It's called empty question mark, okay. This is, so checks that we cannot prove the given goal in the given environment. Relies on a property called negation as failure. The caller has to interpret what this means. So what I mean by this is like, the fact that we can't prove something to be true doesn't mean necessarily it's not true. It depends on your assumptions, right? Like, first of all, your prover might just not be that smart. And so maybe something is provable, but it can't find the right solution to prove it in. Now, in our case, we know that like the ways that Rust can prove things are limited, so we don't have to worry about that. It's considered complete, meaning if there is a solution, it can find it. But even in Rust, though, right, like you can, if you think about a generic function and you have like a type T and you do not have a where clause that T is debug, we cannot prove that T implements debug. That doesn't mean that the type which eventually, you know, with which T is instantiated doesn't implement debug. It just means that there might be types for which it does, and there might be types for which it doesn't. So my point is, the fact that we can't prove things, like you have to, the reason we're kind of careful with this and we don't just want to add a general purpose negation operator to Rust is that you have to interpret it. The fact that you can't prove it doesn't necessarily mean it's not true unless you meet certain conditions. So in the case of coherence, we're kind of careful with how we use it in theory. So now we can add this and say, if we cannot prove this goal, that's good enough for us to say that they do not overlap. That's not the complete overlap rules, but it should be enough to actually accept our test cases, I think. Well, maybe not, because our test case is probably. Why is this not working? Oh, I know why. So we defined this judgment in a different file, but we didn't add it to the export list. So we have to add it to the things that it provides. This file is prove_goal.racket. And now here in this other file, I can require prove_goal.racket, and I can use the name. Okay. And hopefully this error will go away sooner or later. I think our test case probably passes, but it's kind of passing for the wrong reason because we're still not very smart if you have the same impl twice. Like, I think we just accept that all the time. Or maybe it's going to make an error. See what happens. Did something. No clauses matched. Select trait item. Oh, so I added this parameter. So it takes two parameters, the name of the trait and the item, but I didn't add the name of the trait into the second clause. So I couldn't find. So it found that it was not equal here, but it didn't find anything that it matched. That's an annoying thing about Racket. I wish it would detect that the number of parameters did not match. That would be nice. It's pretty basic. So I'm gonna have to run now for the Lang team meeting, but we can follow up more on this and I can push this stuff. Obviously, we're not yet at the point where it kind of works, but I think this is the basic shape we want to have. We're just gonna have to add more conditions later because so this one right now we're able to prove we either accept them if they're exactly equal, which is not quite right. We have to fix that. Or we accept them if the types are not unifiable, which is good. But there are other cases where the types are unifiable, but the where clauses are not provable. And we need to include that. And that starts to get into some interesting orphan-like rules, right? Where that has to be, what does it mean for the where clauses to not be unifiable? We have to figure that out. And then we would add the negative impl cases, which work a little differently. Right, where we sometimes add like for all this, there does not exist to that and stuff like that. So let's end this recording here and we'll pick up offline on Zulip.
Right.
I guess now I realize last thing I'll do is we don't actually need the by formulas we don't need in this particular case because those would be useful if we were going, we'll need them in other ones where like if the parameters are unifiable, we'll need them so that we can go find if any of the where clauses cannot be proven. But in this case, we don't need them. All right. Bye. Thanks. I'll upload this video.
Thank you. Bye.
Thanks. Bye-bye.